NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again.
Now, the universe whispers secrets and numbers so vast that they defy comprehension.
For 45 years, it drifted silently through the dark, far beyond planets, past the sun's last breath, where no signal had ever gone before. Then it heard something, or perhaps sensed something. Now, a Nobel Prize-winning scientist has stepped forward to confirm what many thought was impossible. Voyager 1 has encountered a cosmic mystery that defies explanation. Launched during a once-in-a-lifetime planetary alignment, the spacecraft was never supposed to come this far. And yet, it has. What it's found out there, so far from Earth that light itself takes nearly a day to arrive, has left scientists stunned. Is it a fluke of deep space physics? A whisper from the galactic unknown, or something much more profound? Whatever it is, one thing is certain: Voyager 1 has crossed more than just distance. It's crossed a boundary we never expected. A once-in-a-lifetime planetary alignment. In the mid-20th century, NASA scientists recognized a rare and extraordinary opportunity: a planetary alignment of the outer planets, Jupiter, Saturn, Uranus, and Neptune, that would occur in 1977. This specific formation, which happens only once every 176 years, provided the perfect window for a spacecraft to perform a gravity-assisted tour of the outer solar system. Instead of sending multiple missions over several decades, NASA could launch a single mission, Voyager, that would use the gravitational pull of each planet to slingshot itself toward the next. This innovative concept dramatically reduced travel time and fuel requirements, making a mission to distant planets not just possible, but practical. This celestial configuration, often referred to as the Grand Tour, allowed Voyager 2 to visit all 4 gas and ice giants within just 12 years, an incredible feat given that the same journey without these assists would have taken over 30 years. NASA seized this opportunity with the twin Voyager spacecraft, launching them in 1977. Voyager 1 focused on closer observations of Jupiter and Saturn, including a pivotal flyby of Titan, while Voyager 2 extended the mission by continuing on to Uranus and Neptune. Without the precise timing of this alignment, such an ambitious journey would have likely been financially and technically unfeasible. The use of gravity assists, gravitational slingshots, was a revolutionary application of celestial mechanics. By flying past a massive planet like Jupiter, the spacecraft could have borrowed some of the planet's orbital momentum, increasing its speed and altering its trajectory without burning additional fuel. This technique not only sped up the Voyagers, but also gave office planners a way to refine their trajectory for maximum good encounters with multiple targets. It was a stunning demonstration of how cleverly harnessed planetary positions, albeit following predictable orbital dynamics, can create unique opportunities for exploration. The victories of the Voyager missions only laid proof of how immensely valuable timed planetary arrangements are in deep space exploration. The missions set the stage for many of NASA's subsequent voyages across the solar system and beyond. Whereas such phenomena as planetary alignments may appear to a casual skywatcher only as wonderful sights to behold, they signify rare opportunities for mission designers and astrophysicists that can actually influence the very fabric of knowledge in the universe. The Grand Tour stands as an eloquent testimony of how planning, timing, and natural forces coalesced into one of humanity's greatest achievements in exploration. Their journey started together, but what separated them wasn't distance, it was purpose. Voyager 1 versus Voyager 2. Voyager 1 and Voyager 2, launched just weeks apart in 1977, were part of NASA's ambitious mission to explore the outer solar system. Despite Voyager 2 launching first on August 20th, Voyager 1 followed on September the 5th and reached Jupiter sooner due to its faster, more direct trajectory. This was no accident. The spacecraft was deliberately assigned different paths based on scientific priorities. Voyager 1 was placed on a trajectory designed to make a closer approach to Saturn and its largest moon, Titan, considered a high-priority target due to its thick atmosphere and potential for complex chemistry. The decision to send Voyager 1 past Titan came with trade-offs. In order to reach Titan at the optimal angle for detailed observations, Voyager 1 had to forgo the opportunity to continue on to Uranus and Neptune. This meant its planetary mission would end at Saturn. On the other hand, Voyager 2 followed a longer path that allowed it to complete the so-called Grand Tour, visiting all 4 outer gas and ice giants: Jupiter, Saturn, Uranus, and Neptune. This made Voyager 2 the only spacecraft in history to fly by the latter 2 planets, capturing data that remains foundational to our understanding of those worlds. The 2, almost identical spacecraft were sent on separate trajectories to maximize scientific return. During Titan, Voyager 1 provided much-needed insight into a moon covered in haze. Voyager 2 visited Uranus in 1986 and Neptune in 1989 for the first, and to date, the only, close-up examinations of these remote, mysterious planets. Such a division of mission responsibilities was crucial in an era when limited finances and technology made the concept of launching multiple specialized probes impractical. For the past 40 years and counting, both Voyagers have traversed through interstellar space and continue to relay data back. As energy depletion becomes a critical issue, NASA has started to shut down some instruments to extend the life of each spacecraft. Yet together, their seemingly opposing paths illustrate the brilliance of NASA's mission design. Voyager's unique roles, determined by diverging trajectories, have forever given humanity an unparalleled dual perspective upon the solar system and now beyond into the galaxy. How Voyager was built to last. Voyager 1's extraordinary endurance is largely owed to the ingenious choice of power source, radioisotope thermoelectric generators, RTGs. At a time when solar panels were a standard feature for space missions, engineers understood that Voyager's deep space trajectory would render solar energy insufficient. RTGs, which convert the heat from decaying plutonium-238 into electricity, were selected to provide a steady power supply for decades. This choice ensured that the spacecraft could continue operating far beyond the reach of sunlight, a critical factor that has kept its instruments running in the cold, dark expanse of interstellar space. Durability was a cornerstone of Voyager's design philosophy. Unlike modern consumer electronics optimized for performance and compactness, Voyager 1 was built using tried and tested components that prioritized resilience over sophistication. These parts were engineered to survive harsh cosmic radiation, extreme temperatures, and the vacuum of space without the possibility of repair. Even radiation shielding, some added as late as just before launch, demonstrated the mission team's adaptive thinking in protecting sensitive systems for the long haul. It is another feature of the Voyager mission that efficiency characterized every one of its components. The systems were configured to use minimal power consumption so that the limited radioisotope energy provided by the RTGs could run long-term operations. The spacecraft's onboard memory of approximately 69 kilobytes would today qualify as ancient, yet the architecture has been extremely effective. Smart power management and low-energy consumption protocols allow Voyager 1 to continue functioning even in a dwindling power environment. The spacecraft exemplifies what efficient engineering allows, getting things done with minimal resources. Voyager 1's 3.7-meter high-gain antenna and the accompanying radio system were vital for communicating from such vast distances, that is, now over 24 billion kilometers from Earth. This distinguished dish is forever aimed at Earth by the Attitude and Articulation Control subsystem, continuously sending signals with a transmission delay of over 22 hours. Redundancy in the thrusters, onboard computers, and core systems stands to prove that parts and systems were expected to fail and thus were made able to adapt and keep working. Its very long life and continuing contribution to science speak not just for NASA's design practice, where consideration is always given to what might fail and what alternative pathways might remain open, but also for NASA's engineering, which is both careful and visionary. RTGs and deep space survival. One of the most critical innovations that made the Voyager missions possible was the use of radioisotope thermoelectric generators, RTGs. Unlike solar panels, which lose efficiency the farther a spacecraft travels from the Sun, RTGs provide a consistent power source by converting heat from the radioactive decay of plutonium-238 into electricity. This made them the ideal choice for the Voyager probes, which would travel far beyond the solar energy-rich inner planets into the cold, dim reaches of the outer solar system and beyond. Even after nearly 5 decades in space, these nuclear batteries continue to power key instruments and maintain communication systems, a feat that underscores their incredible reliability and efficiency. The longevity of Voyager's RTGs remains one of the clearest demonstrations of how essential long-lasting energy sources are for missions in extreme and remote environments where solar power is ineffective. RTGs operate using the Seebeck effect, a phenomenon in which a voltage is generated when there is a temperature difference across 2 dissimilar conductors. Inside each RTG, the plutonium-238 fuel emits heat as it undergoes radioactive decay. This heat warms one side of specially selected thermocouples, while the opposite side is exposed to the deep cold of space, creating the necessary temperature gradient. The resulting electrical current powers the spacecraft. The beauty of this design lies in its simplicity. RTGs have no moving parts, which significantly reduces the risk of mechanical failure and enhances their longevity in the harsh vacuum of space. 3 RTGs were installed on each Voyager probe at the time of its launch, which made up a total of about 470 watts of power output. This amount has gradually decreased over the years due to the decay of plutonium, but it has been sufficient to run critical systems. Power has always been rationed by intelligent sequencing of instruments and subsystems, a practice NASA has further developed as power availability dwindles. Despite these inadequacies, Voyager 1 and Voyager 2 can still deliver data retrieved from even the farthest stretches of human exploration, a true feat of engineering and thoughtful design. RTGs have always formed a significant part of any future legacy meant for deep space exploration. As such, their continued performance and successful operation are inextricably tied to the success of the Voyager missions. Today, RTG technology remains at the center of missions traveling from their host sun, like those to Mars Curiosity and Perseverance, and will continue to be very relevant in future missions to outer planets and their moons. The reliability of RTGs, based on previous experience gained in space use, ensures that when science opens more and more distant frontiers, exploration would not stop at the limits of solar power. Thus, the end of dry space as marked by the Voyagers is lit by warm glow, the ungraceful decay of an isotope, in what could be termed an elegant solution to the problem of cosmic endurance. Volcanic surprises and faint rings. Voyager 1's historic flyby of Jupiter in 1979 marked the beginning of an extraordinary chapter in planetary exploration, revealing a dynamic and active system previously hidden from human eyes. Among the most groundbreaking findings was the discovery of active volcanism on Io, one of Jupiter's largest moons. This was the first time such geological activity had ever been observed beyond Earth. High-resolution images captured towering volcanic plumes rising hundreds of kilometers above Io's surface, revealing it to be the most volcanically active body in the solar system. The intense activity is caused by tidal heating, a result of gravitational interactions between Io, Jupiter, and neighboring moons, a phenomenon that fundamentally altered our understanding of how energy can shape planetary bodies. Europa, another Galilean moon, also captivated scientists during the flyby. Though its surface appears deceptively smooth and icy, Voyager 1's imagery showed a landscape etched with long intersecting lines and very few craters, hinting at recent resurfacing. These features pointed to the possibility of a subsurface ocean beneath the icy shell, one kept warm by similar tidal forces that power Io's volcanoes. The idea that Europa might harbor a liquid ocean beneath its crust raised the tantalizing possibility of extraterrestrial habitability and inspired future missions aimed at exploring its potential for life, such as NASA's forthcoming Europa Clipper mission. Besides changing our perspective about moons of Jupiter, the spacecraft also stumbled upon something rather enigmatic with respect to the planet itself: a fine ring system. From before that point, it was only Saturn thought to wear rings. Voyager 1, the instruments found and recognized fine, dusty rings around Jupiter, invisible from Earth because of their thinness and unreliability of reflection. They are made of tiny particles expelled by impacts striking Jupiter's small inner moons, trapped in orbit with vast gravitational pull of Jupiter. The finding thus transformed our knowledge of how common and varied the ring systems can be in the solar system. Voyager 1 conducted extensive studies of both the moons and the rings around Jupiter. It also went into the strong and wide-ranging magnetosphere of the planet. The resulting observations showed that Jupiter sports the strongest magnetic field of all planetary bodies in the solar system. Indeed, it extends millions of kilometers into space and traps charged particles in very intense radiation belts. Those very belts interact with particles of Io emanating from volcanic eruptions, bundling around the planet in a plasma torus. The event accentuated the great intensity of the control that is exercised over the geological and electromagnetic realms by interconnected relationships between a planet and its moons. The success of Voyager 1 by flyby set up a new benchmark of severity in planetary science that revealed Jupiter to be a world of extreme forces and surprising complexity. But just as Voyager 1 was wrapping up its revelations at Jupiter, the next stop would unveil something even more alien and far more mysterious. A close look at a hazy world. Voyager 1's close encounter with Saturn in November 1980 delivered a trove of discoveries that transformed humanity's perception of the ringed planet and its expansive system of moons. During its closest approach, just 124,000 kilometers above Saturn's cloud tops, the spacecraft captured detailed images of the planet's iconic rings, revealing features such as spiral density waves, radial spokes, and intricate braids. These structures pointed to the subtle but powerful gravitational interactions between Saturn and its nearby moons, offering early evidence of how celestial mechanics sculpt planetary ring systems. Voyager 1 also provided critical data on Saturn's atmosphere, which appeared to be layered and banded like Jupiter's, though less colorful due to a deeper haze and a lower proportion of helium, which may be sinking toward the planet's core and releasing excess heat. Perhaps the most scientifically significant target of the Saturn flyby was Titan, Saturn's largest moon and one of the most enigmatic bodies in the solar system. Voyager 1's trajectory was specifically chosen to ensure a close flyby of Titan, whose thick, orange-colored atmosphere was believed to resemble early Earth's. During its flyby, coming within just 6,190 kilometers of the Moon, Voyager 1 used radio signals and ultraviolet spectrometry to analyze Titan's atmosphere, since its dense haze prevented any direct imaging of the surface. The data revealed a rich nitrogen atmosphere laced with methane and complex hydrocarbons, along with pressure levels greater than Earth's. This was a groundbreaking confirmation that Titan was the only moon known to have a thick atmosphere, raising new questions about its chemistry, weather, and potential for prebiotic processes. Perhaps the coldest temperatures ever measured on Titan at negative 180 degrees Celsius were still warm enough to keep methane from freezing solid. The hydrocarbons in Titan's atmosphere led scientists to suspect the existence of lakes or even seas of liquid methane or ethane. Such an occurrence would signify an entirely foreign hydrological cycle on Titan. Voyager 1 was able to acquire few insights into the surface features because of the haze, but the information gained helped in planning for follow-up missions, most notably the Cassini-Huygens mission, which later provided confirmation of methane seas. It was those findings by Voyager that set the stage for the speculation of life developing in such radically different conditions, ones that would be solvent systems based not on water, but rather on liquid hydrocarbons for conducting its chemical reaction. Having completed its momentous flyby of Saturn and Titan, Voyager 1 was then steered out of the plane of the solar system, a route optimized for Titan studies but that precluded any further encounters with planets. Although it implied the end of the planetary tour, for mission planners, the large amount of new information that had come from Titan was worth the sacrifice. Now that the work of finding and observing planets was finished, Voyager 1 turned to its new task of exploring the limits of the solar system and beyond. The journey after Saturn marked the adaptability and foresightedness of the mission, signifying that exploration is more than just the reaching of the next point on a map, but rather a deepening of our understanding of the cosmos at every step along that journey. Voyager 2's solo journey to Uranus and Neptune. Voyager 2 embarked on a unique and historic path that set it apart from its twin, Voyager 1. After its encounters with Jupiter and Saturn, Voyager 2 was the only spacecraft to continue its journey deeper into the solar system, visiting Uranus in 1986 and Neptune in 1989. This extension of the mission was made possible by the rare planetary alignment of the late 1970s, allowing the spacecraft to leverage multiple gravity assists. On January 24, 1986, Voyager 2 made its closest approach to Uranus, flying just 81,500 kilometers above the planet's cloud tops. Despite Uranus's bland appearance in visible light, the spacecraft made several critical discoveries, including the planet's extreme axial tilt, approximately 98 degrees, which causes it to spin on its side. This tilt results in bizarre seasonal variations that have intrigued scientists for decades. Voyager 2's observations of Uranus also revealed a magnetic field that was highly tilted relative to its rotational axis and offset from the planet's center, suggesting a complex internal structure. Additionally, the spacecraft discovered 10 previously unknown moons and 2 faint rings, expanding our knowledge of the Uranian system. One of the most remarkable moons studied was Miranda, whose jumbled terrain featured massive cliffs, deep canyons, and surface patterns that hinted at past geological upheaval. These unexpected features on such a small moon challenged assumptions about icy body formation and thermal evolution, pushing planetary geologists to reconsider how even relatively modest celestial objects could exhibit such dramatic internal activity. Its final planetary appointment was Neptune, the most exterior to the main planets. The spacecraft accomplished a near flyby on August 25, 1989, at an altitude of nearly 5,000 kilometers above the cloud tops of Neptune, capturing a completely deep blue world starved with no doubt a great deal of turbulent atmosphere in the haze above it. Images of the interior best show such wonders as the discovery of the Great Dark Spot, a very gigantic amount of storm, almost as large as Earth. Indeed, Voyager 2 recorded the fastest winds in the solar system, scouring at over 2,000 kilometers per hour, in spite of Neptune being so distant and very cold again. Nature very much awful surprised scientists, having expected such a relatively inactive condition in such a distant planet. But perhaps its most dramatic, its most exciting encounter at Neptune was this most detailed exploration of Triton, the biggest of Neptune's moons. Its retrograde orbit about in the opposite direction to Neptune's own rotation thus much suggested that it was a captured object, perhaps from the Kuiper belt. More astonishingly, Voyager 2 witnessed geysers of nitrogen erupting from Triton's surface, one of the earliest views of a putative type of cryovolcanism in the solar system. These forms of activity, together with its small atmosphere and past geological scorching of the surface, reaffirmed Triton's status as one of the most exciting moons in the solar system. Voyager 2 crossed Uranus and Neptune, and in so doing, it not only completed the Grand Tour, it also permitted all humanity the first and only sight ever delivered of one remote outer area of the solar system in close-up sight that serves even today as a measure of rival greatness. Reaching the edge of the Sun's influence, the heliosphere is a vast region dominated by the Sun's solar wind and magnetic field, forming a protective bubble that encases the entire solar system. It serves as a shield against galactic cosmic rays, shaping the space weather environment experienced by all the planets and smaller bodies within its boundaries. This immense bubble stretches well beyond the orbit of Pluto and represents the domain where the Sun's influence is stronger than that of the interstellar medium. At the outer boundary of the heliosphere lies the heliopause, the critical threshold where the solar wind slows, weakens, and finally gives way to the forces of interstellar space. It is here that the Sun's protective reach officially ends. NASA's twin Voyager spacecraft are the only human-made objects to have crossed this threshold, turning theory into confirmed reality. Voyager 1 crossed the heliopause in 2012, and Voyager 2 followed in 2018. These crossings offered scientists the first direct observations of this boundary and gave rise to a new era in heliophysics. As they passed through, each spacecraft recorded a sudden drop in solar particles and a corresponding spike in galactic cosmic rays. Additionally, subtle changes in the direction and strength of the magnetic field confirmed they had entered a new and distinct region of space. These transitions provided empirical proof that the Sun's bubble had a definite edge, a fact once debated in space science circles. Before reaching the heliopause, both the Voyager spacecraft had to cross the Helios Heath, an agitated and chaotic region where the solar wind, having slowed to subsonic velocities at the termination shock, collides with particles from the interstellar medium. Rather than being a smooth or static region, the Helios sheath is awash with swirling magnetic fields, variable particle densities, and complex interactions. The Voyagers found that this region was not just a land bridge, but a dynamic interface where solar and galactic forces meet and merge. The intensity and variability observed in this region challenged the existing models, suggesting that the heliosphere's boundaries must be influenced by conditions of the wider galaxy, and not just by variations in solar output. The data collected from Voyager 1 and 2 have proven invaluable in fine-tuning scientists' understanding of the structure of the heliosphere and the greater context of its relevance to the solar system. These observations contribute to a model of how the Sun's magnetic bubble interacts with galactic forces and how it reacts to changes in these forces over time, including perturbations due to solar cycles. The knowledge gained from the Voyagers, however, has applications that go beyond mere interest. The practical side would be quite pertinent should any future missions send humans or robotic explorers beyond the inner planets. While these two aging warriors continue to forge ahead, there shall exist no other view ever for humankind into where the Sun's influences really end and the interstellar frontier begins. Crossing into interstellar space. On August 25, 2012, Voyager 1 became the first spacecraft to cross the heliopause, officially leaving the heliosphere and entering interstellar space. This historic moment marked humanity's initial step beyond the protective shell of our solar system into the vast and uncharted territory between the stars. Confirmation of the crossing came through a series of compelling data changes. The spacecraft detected a sharp increase in galactic cosmic rays, a dramatic decrease in solar particles, and a notable shift in the direction of the magnetic field. These indicators matched theoretical expectations for what would happen upon breaching the Sun's influence, making it clear that Voyager 1 had achieved something no mission had done before. Voyager 2 made its own crossing 6 years later on November 5, 2018, providing an unprecedented opportunity to compare two separate exits from the heliosphere. Unlike Voyager 1, Voyager 2 had a functioning plasma instrument at the time of crossing, allowing it to directly measure the density, temperature, and velocity of the surrounding particles. This critical data confirmed that the spacecraft had transitioned into a cooler, denser region, further validating the boundaries outlined by Voyager 1. Voyager 2's readings showed that the heliopause is not a smooth or uniform line, but a jagged and fluctuating boundary shaped by solar activity and the interstellar medium's shifting pressures. This reinforced the understanding that the Sun's reach ends in a dynamic, not static, fashion. Both spacecraft are still functional in interstellar space. They still receive and transmit scientifically useful data, albeit at very low data rates and huge distances, with Voyager 1 currently over 24 billion kilometers from Earth, and trailing just behind Voyager 2 at around 20 billion kilometers. The instruments that are still operational are being used to sense cosmic ray intensity, magnetic field orientation, and plasma wave activity. These are the real-time observations of the interstellar medium, which are helping carve out a whole new domain of space science that does not only study our solar system, but also studies its position in the galaxy. A mission for planets was transformed into an interstellar pioneer. The importance of the Voyager's entry into interstellar space cannot possibly be overstated. These tiny vessels, so designed and launched almost half a century ago, have now entered an area beyond the reach of any other human-made object. Their respective crossings have been great feats in scientific exploration and engineering endurance. They also symbolize the eternal curiosity of humankind, a will to reach farther and to know more, even in the regions where sunlight barely shines. As the Voyagers move forward into the unknown, they carry not only scientific instruments, but the dream that one day mankind will be able to go and explore the stars. Yet, even millions of miles past the Sun's reach, the Voyagers weren't done making history, a legacy of discovery. Even decades after launch, the Voyager spacecraft continues to revolutionize space science. As they travel farther into interstellar space, Voyager 1 and Voyager 2 are providing the only direct measurements from beyond the heliosphere, the Sun's protective bubble. Their instruments are actively detecting cosmic rays, magnetic fields, and plasma waves, offering new insights into the structure and behavior of the interstellar medium. This data is crucial because it comes from a region no other spacecraft has reached, and it challenges long-standing models of how the Sun's influence tapers off at the edge of the solar system. Voyager's measurements have revealed that the boundary of the heliosphere, the heliopause, is more complex and dynamic than previously understood. Instead of a clear, sharp boundary, the spacecraft detected fluctuations and layers of magnetic fields and particle densities. Voyager 2's working plasma instrument was especially valuable during its heliopause crossing in 2018, confirming that particle density suddenly increased by a factor of 20, solid evidence of a transition from solar to interstellar space. These findings are helping scientists refine their understanding of solar wind behavior, space weather, and the Sun's long-term influence on its surroundings. More than just solar physics, the Voyager probes are really redefining what we know about galactic cosmic rays, the high-energy particles coming from outside the solar system. As these spacecraft moved out of this heliosphere, they experienced increased cosmic ray intensity and yielded a very good sample of how this heliosphere protects inner planets from such radiation. This information will help inform the design of future missions to deep space, since cosmic ray exposure is vital to determining the safety of astronauts and their electronic devices built for long-term exploration. Thanks for watching. If this discovery blew your mind, imagine what's still out there waiting to be found. Don't forget to like the video, subscribe for more space secrets and science surprises, and drop a comment. What do you think Voyager 1 has uncovered? And hey, there's more where that came from. Click the next video on your screen to keep the journey going. See you out there, explorers!